For exam 5 will be on chapter 16 only. And the review document that I'm handing out today is version 2. If there's a version 1 in Brightspace, then you can look at it if you want to, but I'm probably going to stay with version 2 in our review discussions. The other thing coming up is Thursday, we're going to have a lab on the Ka of acetic acid. So prepare that one in your notebook. I just finished grading the kinetics lab, and there were 2 reports missing. So if you're one of those students, then you probably ought to get them in before penalties erase your entire score. All right, chapter 16. Now, I mentioned when we are first introduced to the topic of equilibrium, I mentioned don't forget the procedures for equilibrium. We're going to continue to use those procedures, and in chapter 16, we're going to apply those procedures to solubility of solid compounds. For the most part, we're only going to consider aqueous solutions. So let's get going. When we describe a solubility, remember we would have a solid of some kind, and then it would be in equilibrium. And this, you can think back to the last lab we had, Le Chatelier's principle. The first activity in that lab was the solubility of sodium chloride. So well, let's just use sodium chloride then. And these solubilities are all ionic compounds, metal and nonmetal. So we have the one we used in the previous lab. It would, in aqueous solution, produce these ions. Okay, and then when I first introduced the concept of equilibrium, I mentioned that there were some K values that had subscripts that were reserved for particular types of reactions, and this is one of them. The KSP means the equilibrium constant for the solubility product. Now, if you remember days in math class, a product is multiplication. Quotient is division. So a solubility product implies multiplication only. There's no quotient factor in solubility. And the reason for that is when we write the equilibrium expression, we're only interested in those species that can change their concentration. And these are aqueous sodium and chloride ions. That solid cannot change its equilibrium, so we don't put it in the expression. So that's where we get the product, sodium ions times chloride ions. That's the solubility product, which is another expression for equilibrium. Now, the solubility product is constant for a given temperature. Let me see who just showed up. The other Kaylee. Okay. Let's see. The only one we're missing is Anne. All right. There's a difference between solubility product, which is an equilibrium constant, and the solubility of. Solubility product is a constant for a given temperature. Just like any other equilibrium constant, it's constant under all conditions as long as the temperature doesn't change. But the solubility is another factor that we can derive from the solubility product. And it's usually expressed in terms of, we're going to use S, a small s for solubility. Now, if the S is in parentheses, of course, it means solid. But if it's by itself, we'll mean solubility. And solubility, depending on the reference manual you use, may be grams of solid per 100 milliliters of water. That's one expression for solubility. But that's a little difficult to work with when we're talking about equilibrium. So our solubility is going to be expressed in molarity. That is, moles of the solid that are dissolved in a liter of solution. All right. Now notice that this example, bismuth sulfide, has coefficients of 2 for the bismuth and 3 for the sulfide. And those are derived directly from coefficients of the balanced equation. And we can do that with the solubility product, just like any other equilibrium expression. Again, the solubility product is like any equilibrium constant, and we don't give the units of measure because they can be so complex. I mean, the sky is the limit. And it's usually, the problem is we're multiplying, we're dividing, we're taking things to powers. The units of measure can be all over the place. So we just, for convenience and brevity, we leave the units off and just be very careful about how you prepare the calculation. Now here's a comparison that's important. When we say the solubility product versus the solubility is in how much of a solid can go into solution, whereas the solubility product is a constant for a given temperature. So if we compare solubility products for several salts, can we automatically say that if the solubility product is higher, the solubility is higher for that given salt? In other words, can we order them in, say, the KSP for this one is greater than the KSP for that one? Can we also say that the solubility of that one is greater than the solubility of that one? And the short answer is no, we cannot. But there's a caveat to that, and I'll show you that in just a minute. All right, those are two reasons why we can't. But if you compare KSPs for different salts, and they have exactly the same format as the solubility product. In other words, if the cation has a power of 1 and the anion has a power of 1 for several different salts, then if the KSP for one is higher than the KSP for the other, the solubility for one will also be higher than the other. That's a direct comparison because the solubility products are structured exactly the same way. But if they're structured differently, if they have different powers, then you cannot say that. We'll have examples of that coming up. And for this example, we say the KSP for sodium chloride would be twice the solubility, and the KSP for sodium phosphate would be 27 solubility to the 4th power. Now that's derived from the ICE table, and we're going to do an ICE table in a few minutes so that you can see the relationship there. Solubility products are very well behaved when we put them in our ICE tables. So you may be able to derive these expressions of KSP based on the solubility just from looking at the compound. But they are derived from the ICE table, and that's the safest route to take in order to get the right answer, at least in the beginning. Okay, say we're going to calculate the solubility of silver chloride. Now, in first semester, we had a chart of soluble and insoluble salts. And we said silver chloride was insoluble. Well, that's not precisely, that's not accurate, because even the insoluble salts may be slightly soluble. And in this case, silver chloride is just that. It may be it may be mostly insoluble, but there are always a few ions that escape into solution. And the KSP describes that equilibrium. Well, let's take that one. Silver chloride in aqueous solution. So this would be silver and chloride. Okay. And the KSP is equal to silver to the first power and chloride to the first power. And that value is equal to 1.6 times 10 to the minus 10. All right. So if we're going to calculate the solubility, we set up an ICE table. Well, that was derived from the ICE table. I'm going to show you the ICE table so you can see where that calculation came from. All right, so if we have initial, change, and equilibrium, the initial for silver chloride it doesn't have a value, but we're going to say the change here is it's going to be losing some of that silver chloride to the solution. So if we start off with 0 and 0 in solution, we know it's going to move to the right, and we're going to gain something over here, but it's 1 to 1 to 1, so we're going to lose something over here. So at equilibrium, we will have lost this, but that's not part of the expression, right? So we say, what do we get over here? We're going to get an S and an S. Now in this slide, X equals S, solubility. So that means that this value is equal to S times S, and there you have X times X, or S times X, is equal to 1.6 times 10 to the minus 10. That means X is the square root of 1.6 times 10 to the minus 10. So the solubility is equal to 1.3 times 10 to the minus 5. And that's molar. That's the molar solubility of silver chloride in water at standard temperature, which would be 25 degrees for the standard temperature for solubilities. All right. What would be the solubility of silver phosphate in water? Okay. Now we need to change our balanced equation. Let's make a little bit more room there. And we'll leave the ICE table, but the factors are going to change. So silver phosphate, and you have to know how to write that compound. Phosphate is a -3 charge. Silver is a +1, so we need 3 of those right here. Okay. When that goes into solution, you're going to have 3 silvers and only 1 phosphate. Okay. So that's the balanced equation. Now we can write the expression. Right? If we lose some of this change here, start off with 0 here, how many silvers are we going to end up with? We're going to end up with 3. right? Because the ratio is 1 to 3. So if we lose 1 here, we're going to gain 3 here. But we're only going to gain 1 here. So at equilibrium, we have 3s here and s here. And the expression for that would be third power and phosphate. Okay? That's equal to 1.8 times 10 to the minus 18. Okay? So now what factors do we have here? Well, we would have silver is going to be 3s. So it's 3s to the third power, and phosphate is s to the first power. Okay? So we're going to reduce that. 3 cubed is what? 3 times 3 is 9, and 3 times 9 is 27. 27. S cubed times s is s to the fourth power. Okay? So all we have to do now to find out what s is divide 27 into this value and take the fourth root of it. Okay? So s is going to be 1.8 times 10 to the minus 18. Fix that. Minus 18 divided by 27. And then we're going to take the fourth root. Okay? So you need to know how to work your calculator to find those roots. Because they could be anything. They could be the square root, the cube root, fourth root, fifth root, sixth root. Could be anything. So let's see. 1. There we go. 1.8, 10 to the minus 18. Okay, divide by 27. And then my calculator, I have to convert. I don't have a root for my calculator, so I have to change my root to a power. So the fourth root is the same as taking the value to the 1/4 power. Remember that? For example, if you have the square root of x, that's equal to x to the 1/2 power. Okay, so I'm going to take the fourth root of that value. Let's see, 0.25, and there. So the solubility of silver phosphate is 1.6 times 10 to the minus 5. Okay? So it's slightly more soluble than silver chloride. Just slightly. All right. So what I've tried to show you here is not just the difference in the solubilities, but where these calculations come from right here. 27 s to the fourth that we saw on the previous slide, right down here at the bottom. 27 s to the fourth is where that came from. It came from the ICE table. Okay. All right. Next topic. Let's see. I'll go ahead and erase it all. All right. So these solids are not always going to be placed in pure water solutions. There may be something there already. And this harks back to the last chapter. Maybe it was the equilibrium chapter. We're talking about common ion effect. Is there something in that solution already that's going to influence the solubility of the solid? So we want to compare solubility of silver chloride in water to that of silver chloride in acidic solution. And what we've got is two different reactions where we've got nitric acid, in this case, nitric acid. Now, why did we use nitric acid and not hydrochloric acid? Well, hydrochloric acid has a common ion, and we're going to do that one on the next slide. But this acidic solution composed of nitric acid generates silver chloride solid is in solution, is sitting in that solution, and it's in equilibrium with these ions, just like before. But now we have something else in that solution. We have hydrogen ions and nitrate ions. So if we add those in here, right, in aqueous solution, is a strong acid, so it completely decomposes into hydrogen ions and nitrate ions. Okay. Now in the slide, I put those together, but you can see that if this completely converts, now all we have is this in solution, we have that, and that. And they're all in solution together so they can interact with one another. Cations can interact with anions. So now we've added this cation. What anion is it going to interact with that it hadn't already done? Well, it's already separated from nitrate. So what does it do with chloride? Nothing, because hydrochloric acid is a strong acid. It's completely dissociated. So there's no compound that forms from HCl. It's just in solution as ions. Okay, what about the other way around? This cation with that anion, silver nitrate. You look that up in your solubility table and you find silver nitrate is completely soluble. Well, up to a point, but for our purposes, it's soluble. So there's no interaction there. So what does that mean for the solubility? The solubility of silver chloride will not change because it does not interact to form any type of compound that would shift the equilibrium this way or that way. We have not, in Le Chatelier's terms, we have not effectively stressed the system by using nitric acid. All right. All right. So what would happen if we have silver phosphate in water and we add nitric acid? All right, so I'm going to leave this one. We're going to change this one to silver phosphate. Silver phosphate would make silver and phosphate ions. Okay. So now what's going to happen? Well, you still got this one, and you've got this solid, and these ions in solution. Silver and silver and nitrate are still not going to interact. What about hydrogen ions and phosphate? Remember, phosphoric acid is a weak acid. It goes through three deprotonations. H3PO4 is going to be in equilibrium with one hydrogen and HPO4 minus. And then that one, HPO4 minus, is going to be in equilibrium with this expression, H2, excuse me. And then HPO4 2 minus, and these are all in aqueous solution. And then this HPO4 2 minus is in equilibrium with this one and this here. And each one has its own Ka, right? Ka1, Ka2, Ka3. And we know the relationship of these three. This one is much less than 1. This one is about 5 orders of magnitude less than that one. This one's about 5 orders of magnitude less than that one. So this one, which side does this one want to be on? It wants to be over here, right? So that hydrogen is going to get picked up by that phosphate and make this ion. But this K also says it's going to be this way. So this is going to be picked up by another hydrogen ion. So we've got taken out one, we've taken out a second one to go here, and this one is much less than one, so it's going to pick up another hydrogen, and it's going to go to this one. So eventually, most of what you put in that solution as phosphate is going to end up as phosphoric acid in solution with a little bit of this, a little bit of that, and removed these. So if we're removing this from that equation, which way is it going to shift? It's going to go that way, which will increase the solubility of silver phosphate. Right? So in this case, the use of an acid will increase the solubility. And it has to be an acid where the silver is not affected. Right? If we use silver chloride, then it's going to it may make this more soluble, but it's going to produce a different precipitate. Right? So we have to use nitric acid. Right? And there's that statement. All that stuff I put up here is right there in that one statement. So how does the KSP of silver phosphate in water compare to that of silver phosphate in acidic solution made by adding nitric acid? Right? We just proved that the solubility increases. We've shifted the equilibrium that way. But what does that do to the KSP? Does it affect the KSP? No. KSP is the same, no matter what the solution. KSP is a constant, as long as the temperature is constant, of course. All right. So now we're going to actually calculate the solubility of silver chloride in a solution that contains 4 times 10 to the minus third molar calcium chloride. Chloride is a common ion. There's already chloride in solution. So what is that going to do to our equilibrium, our ice table? All right, let's take a look at it. We have to reconstruct silver chloride here. Okay, so this is our solid, and this is our ion. All right. So what do we have to begin with? Right? When we first put this in solution, there's nothing there. But it's going to move this direction to make some silver and chloride ions in solution. But we don't have any silver there, but we do have chloride. And how much chloride do we have? 4 times 10 to the minus third molar. But since silver is 0 at the beginning, the equilibrium will be to the right. How much is the question? Okay. So if we lose some of this to make one of these, then we're going to have S here and S plus 4 times 10 to the minus third. Okay. Now we can set up our expression for KSP for silver chloride, which is 1.6 times 10 to the minus 10. 1.6 times 10 to the minus 10. And that is still equal to silver times chloride. And in this case, silver is now S, but chloride can do better than that. Chloride is S plus 4 times 10 to the minus 3. Okay? So now what do we get from this expression? Well, we get S squared and we get 4 times 10 to the minus 3 S. All right. You can see right now that we're going to end up with a quadratic. Right? So the question is, how big is S? Is S big enough to influence 10 to the minus 3? Well, what was S? Well, let's back up. Are we expecting S to be larger or smaller than the previous value we obtained? We should expect it to be smaller. So if the solubility was, what was it, 10 to the minus 5, I think. Yeah, 1.6 times 10 to the minus 5 was the solubility in water. 1.6 times 10 to the minus 5 in water. Okay. So if the solubility is going to be a lot less than 10 to the minus 5, it's not going to influence that value very much. So what we can say is, rather than that, we can say, in fact, that should have been, excuse me. We say this is approximately S times 4 times 10 to the minus 3. And that's equal to 1.6 times 10 to the minus 10. Then S, solubility in our calcium chloride solution, let's see, this would be that 1.6 times 10 to the minus 10 divided by 4 times 10 to the minus 3. That should be 0. That should be 0. Okay, so let's see what we get out of that. 1.6 exponent minus 10 and 4 is 3. So this is equal to 4 times 10 to the minus 8 molar solubility. So we've decreased the solubility by 3 orders of magnitude. Let's see. There we go. There's our ice table. Oh, guess what? Did I make a boo-boo? Yeah, I made a huge boo-boo. Calcium chloride, when going in solution, makes twice as much chloride. So this should be 8. This should be 8. Change this to 8. This to 8. And this to 8. So how would I fix this problem? Well, 8's twice as big, so this should be half as much. Should be 2 times 10 to the minus 8. Now let's see if it agreed. Yep. Okay. Details, I'll get you every time. All right. And one other thing you'll notice is 100 milliliters of our solution, calcium chloride solution, doesn't matter because we're already given the concentration. If we were given absolute amounts of calcium chloride and volume, then we'd have to calculate the concentration. But we didn't have to do it this time because we were told the concentration. It's just that I didn't pay attention and correctly report the concentration of chloride ions. Okay. How about calculate solubility of silver chloride and calcium nitrate? Well, the nitrate ion is with silver is still soluble, so it doesn't affect the silver. How does calcium chloride affect the chloride concentration? It doesn't, because calcium chloride is soluble also. So we should get, since there are no common ions, we should get exactly the same solubility as before. 1.3 times 10 minus 5. Wait a minute. Why did I say 1? Oh, I misread it earlier. It should be 3, right? Let me be sure I didn't make a mistake in the slide. Solubility is 1.3 times 10 to the minus 5. Let's go back. Silver chloride in water. Here we go. Yeah, there it is. I was looking at silver phosphate. My mistake. It's 1.3 times 10 to the minus 5. Solubility of silver chloride. All right, now we can continue after this slide. All right. Now what we're going to this involved the solubility of a solid that we put into a solution. Suppose we have 2 different solutions with cation anions in them, and we put them together. We know their initial concentrations. We can calculate their mixed concentrations. How do we determine if the concentration of the anions and the cations is high enough to produce a precipitate? In other words, to go backwards. If we know this concentration and that concentration, can we tell if we're going to get a solid from that mixture? Right? So let's use this silver chloride as an example. All right. If we were to be given concentrations of silver and chloride, and we're trying to decide which way the reaction moves. We're already given concentrations, and one of them's not 0, right? They both have concentrations. Then remember how you tell whether or not the equilibrium will move this way or that way. You generate the Q value. You take those concentrations, plug them into your equilibrium expression, and calculate the Q with the given concentrations. And then you compare the Q. If the Q is greater than KSP, that means these are too big, and it's going to shift this way and give you a precipitate. Precipitation will occur if the Q is greater than the KSP. If the Q is less than the KSP, then you won't get any precipitation. Now, the advantage to this is that we can use that information to separate ions from solution. In other words, if we know we have a mixture of cations in solution, and we know their relative KSPs, we can calculate how much of the anion that will precipitate, some of them, is required, and we can put that minimum amount and get a precipitation from some of our cations. They will drop out of solution. We just filter them. Now we've got a partial separation. That's where we're headed with this idea. Okay. So remember, Qs are calculated with parentheses, not square brackets. All right. What I just described to you is called selective precipitation, where we have a mixture of metal ions and we want to separate them. So we're going to, this example, say we know that there's barium and silver in the solution. Now, of course, cations have to have counter anions, right? You can't have just all cations in solution. Why? Because chemistry, we don't deal with electrostatic charges. Our solutions are neutral always. So if we have a mixture of barium and silver in there, then we have to assume that there's some counter ion in there that generates the solubility of barium and silver. And my guess would be something like nitric acid or nitrate ion, because all nitrates are soluble. But what would happen if we add hydrochloric acid? Adding hydrochloric acid will form a precipitate with silver chloride, but it will not precipitate barium. Barium chloride is soluble. In fact, all chlorides are soluble except for, I think, 3 of them are insoluble. Silver is one of them. And the advantage also is that we're not going to contaminate the solution with other cations. By adding hydrochloric acid, we're only adding the chloride as the common ion to precipitate silver, and the hydrogen ions just make the solution acidic. Right? If we added, say, sodium chloride in there, we could precipitate silver, but now our barium solution left behind is contaminated with sodium. So hydrogen chloride is a better choice. All right. Suppose we have a more complex mixture. We have copper 2 plus, mercury 2 plus, nickel 2 plus, and manganese 2 plus ions. And we want to use hydrogen sulfide. Right? We know that the sulfides of each of these cations is insoluble, but they have different solubilities. They have different KSPs. So we're going to use what we know about their solubilities and the Q value that needs to be used to solubilize some, but not all. Right? We know that at a low pH, sulfide is relatively low. Why is that? All right. Sulfide, hydrogen sulfide in solution will be in equilibrium with hydrogen ions and sulfide ions. Okay? If we have a low pH, let's see, at a low pH, acidic solution, we've got lots of hydrogen ions, right, which drives the reaction back this way. Okay? When that happens, you have very low concentration in acidic conditions. We have low concentration of sulfide. Okay? So the least soluble sulfides of our cations will precipitate because all they need is just a little bit of sulfide and they will come out of solution. Right? So there's the overall K for that sulfide. This is the overall reaction. Since there are 2 hydrogens, we actually go in 2 steps. But for our purposes, the overall reaction works just fine. We know that the overall K is 1.2 times 10 to the minus 20, which means it's very, very insoluble. And we want to reduce its solubility even further by adding acid. Okay? So once we do that, we precipitate. This precipitates mercury and copper. Okay. Now, excuse me, if we add hydroxide to the solution, how are we going to do that without influencing the solubility of the others? Well, if we add sodium hydroxide, sodium sulfide is completely soluble, right? So it's not going to influence the precipitation itself. It'll contaminate the solution, but it won't contaminate the precipitate, right? So if we add hydroxide to that solution, now it's basic, and we have removed hydrogen ions. We're shifting the equilibrium this way. We're making high sulfide. By comparison, high sulfide ions And now we can precipitate the more soluble compounds of nickel and manganese sulfide. Okay. All right. So here's what the flow chart looks like for this particular selective precipitation reaction. All right. We add hydrogen sulfide at a pH of about 2. All right. If we make the pH too low, then there won't be any sulfide in the solution and you won't get any precipitate. So we have to be careful with the pH. About pH 2 will be enough sulfide to precipitate copper and mercury. And then we acidify, we basify, we add hydroxide to about a pH of 8, and that gives us enough sulfide to precipitate the manganese and the nickel. Now we have a partial separation. How do we get the manganese and nickel apart, or how do we get the copper and mercury apart? So this, you can see that this decision tree can branch into lots of different avenues if you're trying to separate individual metals out of solution. And this is what was classically known as bench chemistry. We would do these separations on the bench, wet bench chemistry. Now we can do it, if we want bulk amounts of these metals, yes, we still have to use these methods. But if we're just quantifying the amount of each one of these metals in a given solution, we don't have to do this separation to quantify them. We have other methods that can use smaller amounts, give us very accurate values, like atomic absorption spectroscopy or spectrophotometry, depending on the metal, or inductively coupled argon plasma spectrometry, which is a very effective means of quantifying them. But it's a destructive process, both of them. So if you want to collect these metals in a final solid form, then you have to go through the wet chemistry. All right. So if we have a more complex mixture, like that given in the top, and it's squeezing all this in there makes everything too small. But we have lots of metals up here in this mother solution, and they're color coded so that you can see that the first one is a purple separation for these cations. The next one is kind of a yellowish separation for these cations, then an orange, and then a green, and then a blue. So we're taking these through, these are 5 different groups, 4 steps, 1, 2, 3, 4. Yeah, 4 steps to separate these 5 groups. And I think this this chart is contained in useful information. Let me check to be sure. Let's see here. Yep, there it is. So you will have access to this on an exam. So the first step in separating groups of cations is to precipitate the ones that are insoluble chlorides. Silver chloride, definitely. Lead 2+ chloride, and silver 1 chloride. Remember, excuse me, not silver, mercury. Mercury 1 is like this. Right? That's just the way mercury behaves, right? This is a 2+ oxidation state, and we haven't covered that yet, right? 2+ charge. But if you got 2 of them bound together and they're both 2+, then each one is a 1+ charge. So chloride only precipitates the mercury 1. But all we have to do is add hydrogen chloride, and we can precipitate out these chlorides of silver, mercury 1, and lead. Then, since the solution is already acidic, we add hydrogen sulfide and precipitate those sulfides that are very insoluble. And that includes the yellow group, copper, bismuth, cadmium, lead, mercury 2+. So that's the other ion of mercury. Arsenic 3, antimony 3, tin 3, and tin 4. Those will all come out as sulfides. And then we add our base. We change the pH from about 2 to about 8, and we get we get two types of precipitates here. We will get those that are insoluble sulfides, like zinc and nickel and cobalt and manganese and iron, iron 2+. And we'll also get insoluble hydroxides, aluminum hydroxide, iron 3 hydroxide, and chromium 3 hydroxide. Those will come out when we change the pH to about 8 with sodium hydroxide. And then, since the pH is already basic, we're going to add some carbonate. Sodium carbonate will dissolve in that solution, produce the carbonate ion, and precipitate barium 2+, calcium, and magnesium. And then what we have left in solution are all the alkali metals, right? Sodium, potassium, if there's any lithium there, if there's rubidium, cesium, they will all be in the final solution. They'll be along with ammonium if there's some ammonium there. Now, when we precipitate these metals as their various compounds, their chlorides, their sulfides, their hydroxides, their carbonates, how do you get those out before you add the next step? You simply filter them, right? You pour the solution through a filter that has small enough pores to catch your precipitate, and you take the paper and dry it down, and you've got your solid precipitate. It's still a mixture, but it's not as complex as the original. So in the end, you've got a solution that has the alkali metals and ammonia possibly left over. So how do you get those into the solid state? Right? You just boil them, right? Drive off the water, and you have the solid left over. And then if you want to separate those metals further, you have to go through more steps, and we don't have the time or the inclination to do that in this course. But that's a first series of steps for selective precipitation of cations. Now we're going to shift gears a little bit. We've been talking about solubilities, and we're still going to keep solubilities as a factor. But we're going to introduce this concept of complex ion equilibrium. In this case, all the components, all the reactants and products are soluble in aqueous solution. But they are soluble to the point that they have an equilibrium also with the metal ions and what we call the ligands, those other reactants that are attached to the metal ions that make them soluble as a complex ion. Right? I'll show you an example in just a minute. In order to have a complex ion equilibrium, you need a metal, and the metal ion is going to be deficient in electrons. Right? It's going to have a charge, maybe a +1, it could be a +2, +3, it doesn't matter. For our case, we'll just say a metal ion with a +1 charge. It's electron deficient. Which makes it what? It makes it a Lewis acid. A Lewis acid because it's electron pair acceptor. Okay, that's a Lewis acid. Electron pair acceptor. So we're going to react it with a ligand, which is a Lewis base. It could be more than one, and the ligand could be a negative charge or it could be neutral. Doesn't matter. But it does have electrons that can be donated. It could have a pair, could have two pair, three pair. It varies. So this is our electron-rich species, the ligand. And this is a Lewis base, which is an electron pair donor. Okay? And what we get is an equilibrium setup with the metal and the ligand. If this is neutral, it still retains the charge. But we have a bond, a coordinated bond, where this ligand donates the electron pair itself. Now, it's just an example. This can vary all over the place. Numbers of these, charges here, could be charged there. The sky's the limit. But what we set up is this may be in solution, this is in solution, and this is in solution. Okay? And we set up equilibrium. Now, the equilibrium may put most of our metal and ligand over here, but if we increase the concentration enough here, then we can drive the equilibrium to the right and produce a significant amount of the complex ion. Now, I've got two extra handouts that are also in Brightspace. One is a list of solubility products for the different solids, different salts. And the other one is a handout for naming these compounds. Now we're not going to go through that. We're not going to do nomenclature for these complex ions. It's just too much and beyond the scope of this course. But I thought I'd give it to you anyway, so if you ever run into them, you can decipher the names. Okay, so we've got this complex ion, and if we increase this to enough, right, it will drive the reaction here. And what that does is consume the metal ions here. So if those metal ions are in solution, then we can move them into this complex ion, and we set up an equilibrium. Okay. This has a K value with a subscript of F. That simply means the formation constant or the stability constant. And it's written, like we always do, with products. In this case, it would be that. This on this side, and the ligand on this side. So that would be an example of a formation constant expression. All right. Now, if there's only one of these, then this is complete as is. But if the overall reaction ends up with two or more ligands attached to that metal, then each one is similar to an acid ionization, right? Each one happens one ligand at a time, and each of these has its own K value. So our example here is beryllium and fluoride ions. Eventually, we're going to have 4 fluoride ions attached to that beryllium. And each one of those equilibria as one fluoride, and the second fluoride, the third, and the fourth. They each have their equilibrium constant. And overall, we just multiply all those together, and we get an overall of 10 to the 12th in this case. So what that tells us is that the equilibrium for this particular reaction lies far to the right. Right? That tetrafluoroberyllium 2 tetrafluoroberyllium-2 ion is the final product. And we can see from each step that the equilibrium for each step lies far to the right, far to the right, far to the right, far to the right. So it makes sense that the overall reaction is going to be way far to the right. So all we have to do is add some fluoride to this solution, and it will form a complex ion with beryllium. Okay. So what's the rationale for the solubility of complex ions? Hold that thought. Since we know how to make complex ions now, and we know how to solubilize only slightly soluble solids in water, we know one way. We showed just add nitric acid to silver phosphate and you solubilize it. Okay. So that's one of the strategies. The second strategy is complex ion formation. So you have two possibilities here. If the anion of the solid in solution is a good base, that is a good Bronsted-Lowry base, it's looking for protons, right? It wants protons really bad. Then all you have to do is add protons to the solution, and you will, and that's acidify the solution, and you will increase the solubility of that salt, of that solid. That's attacking the anion to increase solubility. But what if you have something like silver chloride? If you acidify the solution with nitric acid, it doesn't change the solubility, right? Because chloride doesn't want hydrogens. It's a very poor, it's a weak base. Why? Because hydrochloric acid is a strong acid, so the conjugate base is weak. Well, in that case, you can't solubilize silver chloride by attacking the anion. You have to attack the cation. You have to attack the silver itself. And that's where complex ions come in. If the anion is not basic, I mean, it's very weak base, then you form a complex ion with the cation, and you can solubilize them. So if we have something like this, and we can't make it more soluble by removing the chloride ions, then let's remove the silver ions in a form that disturbs, that stresses the system so that it will move this way. And the way to do that is to make a complex ion with silver, because that equilibrium will lie to the right as written. It'll produce the complex ion, remove silver. It's a coupled reaction. You remove silver from this equilibrium, and that causes more silver chloride to solubilize. Now, there are several choices to solubilize silver, but the one we're going to use in the lab, not this coming lab, but the next one after it, where we actually calculate the formation constant for a complex ion with silver, is we're going to use ammonia as the ligand.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure.
You may want to turn your sound up. It's not very loud on my end. And this is going to, this Khan Academy video It's going to rehash some stuff we've already covered, but it will also introduce the concept of complex ions for silver. That's one of the reasons I added this video.
Water, we're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the -10. So we put in here 1.8 times 10 to the -10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the -10. So we take the square root of that, and X is equal to 1.3 times 10 to the -5 if we round that. So X is equal to 1.3 times 10 to the -5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right? So ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. this is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening, right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ICE table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia, so let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is x, and our concentration of chloride anion is also x. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the first power times x to the, let me take that out, times x to the first power, right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
All right. Okay. while Salkan was talking, I was working through the same procedure that he was using on the board. And instead of 3 molar ammonia, I used 10 molar to see what the difference would be. He came up with a solubility of 0.14 molar for silver chloride in a 3 molar ammonia solution. And when you increase it to 10 molar, you get 0.47 molar concentration. So increasing the ammonia increases the solubility of silver chloride. What we have here is kind of a rediscussion. Salkan included the overall ammonia reaction, but this one includes the stepwise reaction of silver with ammonia. And you have the different K values for each one because we have 2 ammonias. Each one adds separately. And each of those Ks has a value. And the overall K for the Kf for the reaction would be 2.1 times 10 to the third times 8.2 times 10 to the third. But then if we want the KEQ, right, we want the overall equilibrium constant for this reaction, which I brought down here, canceled out the silvers. Then we just multiply all those together, and the composite, the KEQ for the overall reaction, is 2.76 times 10 to the minus 3. I think Saul, well, let's see. I used KSP of 1.6 here instead of 1.8. So the numbers are correct with this difference. And you're going to find that when you look up values for solubility in reference manuals, they're going to vary quite a bit. So overall, this slide tells us 2.76 times 10 to the minus third. Overall, for this series of data and values, gives you a 2.9 times 10 to the minus 3. So actually 0.47 wouldn't be accurate, would it? Because 0.47 is a calculation that where I used the 2.76 times 10 to the minus 3. So we'd still set it up the same way, set up the calculations. Right. Instead of, that should be 2.76, shouldn't it? Yeah, that's a typo. Should be 2.76 here. If we used the values in the slide, then we would end up with a solubility of 0.47. There we go. But if we used this one, let me see what we would get. Let me see. We got time? Yeah, we got time. So we're going to take the square root of this. The square root of this is just going to be s over 10 minus 2s. So the square root of 2.9 times 10 to the minus 3, take the square root of that, is 5.39 times 10 to the minus 2 equals s over 10 minus 2s. Okay, so then we bring this one over here, and 10 times that is 5.39 times 10 to the minus 1 minus 2 times that value, or 1.08 times 10 to the minus 1 10 to the minus 1, excuse me, S. Okay, and that's all equal to S. So now we want to get the S's on the same side, right? Bring this one over, the negative changes to a positive, and we add it to S. So it's going to be, this is 0.108. So it would be 5.39 times 10 to the minus 1 equals 1.108 S. And then S is going to be 5. Well, let's put this in standard notation. This will be 0.539 divided by 1.108 equals 0.539. 0.49 molar. Okay. So using this data here, I should get 4.9 molar. Here we go. So it wasn't too far off. Okay. Now, how much ammonia is left in solution? Well, if the value were 0.47 molar concentration, then 0.47 molar is the concentration of silver chloride that goes into solution. And for each one of silver chloride, you get 2 ammonias being consumed. So we're actually using up 2x. So we started off with 10 molar ammonia. Now we're going to minus 2 times 0.49, or 0.47 in this case. And what we end up with is about 9 molar. So you've got a lot of ammonia still left in solution. Now, does that make any sense? Well, let's see. This value is 10 to the minus 3, right? So that means this equilibrium is over here. That means most of the ammonia is still like that, and only some of it is over here. Okay? So as it turns out, there's about 1 molar under these conditions. There's about 1 molar ammonia being used over here, and the other 9 molars is still ammonia. But, and that's why when we solubilize silver by using this equation, by this technique, it takes a lot of ammonia to do it. In fact, in the lab, when you add ammonia to your solution, even after you've added it to the solution and diluted it, you take a whiff and you can still smell the ammonia. Okay, that's the last slide.